All right, next thing, integrators. You know what integration is, hopefully. It's just finding the area under a curve. And there are circuits that can do that. There are op-amp circuits that can do that, actually do it quite well. An integrator is also a type of inverting gain op-amp circuit. So it follows the same exact pattern as what we started with. It's going to have some impedance in the feedback path and some impedance and the input. If you input a sine wave, you'll get out a cosine wave, which is not all that exciting. It's just a sine wave that's shifted by 90 degrees. So that's not so cool. But if you put in a square wave, you'll end up getting a triangle wave, because basically the area under a square wave is going to increase as you go, and what's going to be output is going to be that increasing value, except that an integrator is an inverting circuit. So actually when you have a positive square, you'll have a negative going triangle. And then when you drop down to the negative part of the square, you'll have a positive going triangle because it's an inverting circuit. But this is the difference between integrators and what we just covered. They work over a certain frequency range that depends on the design of the circuit. They don't work at all frequencies. So what do we do? Well, we're going back to the low-pass filter. The low-pass filter, you noticed, passes frequencies at a certain area. They just go right through and they work. But it also integrates at other frequencies that are not used in the low-pass frequency, or the low-pass part. So what ends up happening? If we look at an actual example, and this is probably an easier way to visualize it than to try to explain all the details. So we have, this can be used as an active low-pass filter if you want, and we know how to find the break frequency and the low frequency gain, because we just did that. We can find the break frequency as 15.91 hertz, so that's really, really, really low, and we can find the gain of 40 dB. And we can plot that. And we can plot the output, and you notice that the break frequency is right there as we expect. And the gain is 40 dB. And what we're going to do is we're just going to divide this up. So if we were going to use this as a low-pass filter, we couldn't go past about 16 hertz, which, you know, is super low. But that's the way it's being designed. So we call that part the pass band. The other part, where that slope is, that is where you actually have integration. That's where the circuit integrates. Anything above that 16 hertz, where that slope is, that's where the integration happens. And what's more, that part, the integrating part, can also be divided up into two parts. So we can look at where in the circuit the gain is 0. So you notice over to the left there is a place where it's a 0 dB gain. We're going to kind of mark that. And any frequencies that occur below that mark will have a positive gain and get bigger. Anything that occurs at frequencies higher than that mark will have an attenuating gain. They'll get smaller. They'll still get integrated, but they'll get smaller. And so what ends up happening is we want to know what that frequency is. Where does that actually occur? Where's that dividing line between the signal that gets bigger and the signal that gets smaller? Or maybe we want the signal to be exactly the same magnitude when it comes out and when it goes in, which is kind of hard to achieve, but can be done. Well, we calculate that frequency right there, and we call that the unity gain frequency. It actually has more than one name, but I'm only using it as a unity gain frequency right now. The unity gain frequency is what is going to determine kind of how we design the circuit. It's an important parameter, but it is not the only parameter at which integration occurs. It's just kind of a dividing line between when the gain is positive and when the gain is negative. So we know how to find the break frequency, but how do we find the unity gain frequency? Well, we set the magnitude of the gain to 0 dB. So we already know what the gain of this circuit is because we already did that last time. So 0 dB is 1, so we take that gain equation and we set it equal to 1. Now, omega R2C squared is way, way bigger than 1. So we're actually going to leave the 1 out. It makes the math a whole lot easier. So we actually kind of neglect that 1. So we say that that's approximately equal to R2 over R1 omega R2C. And now you see you can actually take the R2s out. And so we get 1 over R1 omega C equals 1. Then we just solve for the frequency at that point, and the unity gain frequency is 1 over R1C, which means that we're using that other resistor. We used one resistor for finding the break frequency, and we used the other one for finding the unity gain frequency. So the two that are together, that are physically connected, the capacitor and resistor that are connected, they determine the low or break frequency, and then the other two determine the unity gain frequency. That's probably the point of greatest concern or confusion for students, is remembering which is which. But if you think about how a low-pass filter is laid out, the low frequency is going to be the break frequency. The unity gain frequency is going to be a higher frequency than that, so you'll end up automatically with those values. So those are the two frequencies that actually matter. We calculate 1 for break, we calculate 1 for unity gain, and then we go and just kind of figure out what we're going to do with this. Because that's not the only thing. We know we can figure out the gain, but how do we figure out exactly what we get out of the circuit? Because the waveform is going to change. How do we know and how do we predict exactly what we're going to get? So basically what we can do is look at a general formula and then try to make it specific. So a general formula to integrate is just minus 1 over R1C times the integral of whatever Vn is. That's what ends up being how this works, because minus 1 over R1C is how we kind of used and determined what the gain was and the 0 dB gain and all that. So that's going to be what raises or lowers the value. And we get different results depending on what kind of waveform we use. So we're going to look at 2 simulation examples and illustrate how this is done. And when you do lab next week, you'll do the same kind of thing, and you'll have some waveforms to play with. And beware that lab. I think I ended up stretching out that particular lab, next week's lab. You have actually 2 weeks to do it, just to make sure you get it done, because sometimes it gets long. So we're going to look at 2 examples. And we have numbers already, and we're going to give a value for Vn, and Vn is going to be 1 times sine 2 pi 1000 t. So we're going to look at just the sine wave first, and we can find the unity gain frequency really easily by taking 1 over 2 pi 10k times 10 nanofarads, and we get 1.592 kilohertz. And we're going to we looked at this before, so we're going to look at the plot that we had for that circuit before, and we can expect at 1 kilohertz, we expect to have a gain of about 4 dB, because we can look at the graph and say, okay, that's where we are on that line, and we should expect that value to come out. And we should expect that that's what we get. And we're going to see what we do end up getting. So we take the waveform, and we go ahead and put it into our equation. We just have sine omega t. We don't worry about what the frequency is right now. And we just go through and we do the integral. So we pull out minus 1 over omega. We get a cosine instead of a sine, so that's how we integrate that. And we don't worry about constants, Constants would be DC values, and we don't worry about that. So we don't worry about any integration constant here. We're just getting an idea of the shape. And then we just put all the numbers in and calculate. And when we do that, we put all the resistor values in, we put the value of the frequency at which we're operating, and we go through, and also we convert it back to a sine wave, because what we want to see is how it compares to the original. So instead of having a cosine wave at the end, we're actually going to have a sine wave plus 90 degrees. And what we end up with is exactly 1.58 times sine 2 pi 1000 t plus 90 degrees, which means that we end up with exactly what we thought we would. We end up with the right gain, and we end up with the right shift. So the sine waves aren't so interesting because they basically come out looking like sine waves again. Square waves are much better. Square waves are more interesting. Square waves are kind of where it's at. So we want a 2 volt peak to peak, 1 kilohertz square wave. And in this case, we're going to do the same thing again. We just have minus 1 over R1C times the integral of Vn. And what that means is we have minus 1 over 10K times 10 nanofarads because times whatever the area under that would be. And the way we figure that out is we plot it. And if we look at the positive part of the waveform kind of shaded in, we just want to know what that area is. And we have to pay attention to, first of all, you have to pay attention to the fact that the time is in milliseconds, not seconds, so we have to take that into account. And other than that, we just multiply together, and we take the negative and we multiply, and we get minus 5 volts as the output. And what this means, this will be a 5 volt peak to peak inverted triangle wave out. That's what we expect. And when we go through and look at that, that is actually what we get. And you'll notice that the positive part results in a negative slope, and that's because of the inverting nature of the amplifier, and vice versa. Other than that, this is working exactly as it should.